Hello everyone, welcome to my presentation. Today my topic is related to the Apple Bluetooth subsystem. The title is Attacking IOBluetoothFamily HCI and Vendor-Specific Commands. My name is Wang from DD Research America. I can be reached through this email address. In the first part of the presentation, we will focus on the design and the implementation of Bluetooth HCI on different platforms. The first question we may have is, what is the HCI of the Bluetooth system? Basically, people define the operating system side as the host and the firmware side as the controller. Then, the software interface between the host and the controller is called HCI. From the hardware perspective, the physical connection can be, for example, the UART interface. The following is a more detailed diagram. The blue part here is the HCI stack, which includes components such as daemons and drivers. The red part is the HCI firmware, or we can call it the controller. The yellow arrow is HCI, which is a bridge connecting the two parts. For daemons, HCI provides a unified command method to access Bluetooth hardware features. The next question we may have is, how many commands does Bluetooth HCI support? The answer is a lot, and they are divided into many groups. It is worth mentioning that there is a group dedicated to vendor-specific commands, or we can call it VSC for short. If we search for VSC on the internet, we can quickly find documents similar to the following. This document is from Texas Instruments. But I have to point out that only a small number of Bluetooth vendor-specific commands are documented. For most of them, we cannot find references at all. Another thing is that the meaning of VSCs on different hardware may be different, even if their opcodes are the same. For example, for the command whose opcode is FC0A, they have completely different meaning on the TI and Broadcom platform. And let's take an example to learn the HCI command of Bluetooth. In the link control group, the number one command is inquiry. We can find its definition in the latest version of the Bluetooth official manual. According to the manual, inquiry must include lap, inquiry length, and the number of responses. The manual also defines the correct value range for input. For example, for inquiry length, input should be from 1 to 30 in hex. If you submit an incorrect input, it will theoretically be rejected by HCI or controller. With the basic concept of an inquiry command, let's take a look at how each operating system implements it. I chose 3 different operating systems: lightweight Bluetooth, Linux kernel, and macOS kernel. Lightweight Bluetooth is representatively implementation of Bluetooth protocol stack, and we often see such lightweight implementations in IoT devices or IoT environments. Lines 731 to 738 of the code are the construction of the inquiry command. We can see that this code is constructing lab, inquiry length, and the number of responses almost byte by byte. Personally, I don't like this kind of handmade code very much. They are not easy to maintain and sometimes not easy to understand. When it comes to the Linux kernel, it becomes clear. Almost all commands are defined as data structures, which can be found in the header file. The third example is our protagonist today, the macOS IOBluetoothFamily kernel extension. When I first located the function IOBluetooth HCI inquiry, I saw some strange strings. With the deepening of reverse engineering, I found a large number of such strings, which appear in almost every Bluetooth HCI handler. Curiosity drove me to summarize these strings, and I found that they could actually be regarded as indicators to guide the functions packed data list and unpacked data list. The indicator for Bluetooth HCI inquiry is HBTBB. H means 2 bytes, and B means 1 byte. They represent the opcode and body size of the HCI request. TBB corresponds to LAP, inquiry length and number of responses in the menu. So we can easily deduce that T means 3 bytes. Now we can summarize 3 different operating systems. The implementation of IoT-related HCI represented by LWBT is the simplest, and the design of macOS IOBluetoothFamily is the most complicated. I think Apple can patent their HCI request construction process, maybe. Second, complex design often means more attack surface. And please also keep in mind, if the design and the implementation are too simple, it usually doesn't mean security. We will discuss it later on. In the next part, we will try our best to dive into IOBluetoothFamily. To be honest, when I started this research project, I didn't expect that I could find the security problems of Bluetooth. At first, I just want to learn about the Bluetooth subsystem of macOS. For this, I read the documentation, read a lot of source code, and even reverse engineered the Bluetooth kernel extensions. However, if we in turn to take the previous work as a starting point and continue this research seriously, where should we start? For me, I think I still need some more tools. For example, Sniffer. I need Sniffer. I need fuzzer. I need the code coverage methods for closed source driver and the kernel address sanitizer. Then we need to do attack surface assessment. After reverse engineering, I found that there are at least 2 attack surfaces that we must consider. Simple dispatch WL is responsible for managing the data flow from daemons to the HCI, while the function process event data WL is in charge of the state machine from the controller back to the host. And 3 years ago, in order to learn macOS, I wrote a kernel extension which integrated file operation monitoring, dynamic library, and network traffic monitoring, mandatory access control policy filtering, kernel extension firewall, and other features. The project called Kimon also includes a kernel inline hook engine, which can hook almost any kernel function you want. The source code of the project can be found on GitHub. In the last year, I practiced macOS IPC communication monitoring based on this project. It can filter XPC, IPC communication between processes. And here is a link to Black Hat USA Arsenal. And in order to learn more about the architecture and the attack surface of macOS Bluetooth subsystem, I wrote several sniffers based on KMon. This screenshot is one of them. It can intercept all HCI requests sent to the controller. Because KMon has pre- and post-callback capabilities, I can parse out the input parameters, call processor, like Bluetooth D, and other useful information in the pre-callback handler. And I can also print or modify the return data of the target function in the post-callback handler. By analyzing the log, we can find some interesting details of the Bluetooth operation on macOS platform. First of all, every specific operation is accompanied by create and the delete operation. This is very similar to the file operation, file open and close handle operations on Windows platform. Between create and delete is a specific HCI request. And I have a demo of the Sniffer project. Please let me play the video. Let me first clean all KMon logs. Then I will turn on AirDrop. It will trigger sharing D and Bluetooth D's operations. Okay, yeah. Then we can see a large number of Bluetooth HCI requests. Let's take the first group. The first group as an example. First is the create operation, and then is a raw vendor specific command from process Bluetooth D, and then is a delete operation. So compared with other HCI sniffers, KMon-based sniffer can capture and display the details of these core sequences. Okay. And in order to deepen our understanding of the HCI commands, we need to do some more practice. Next, I'd like to refer an article called Hacking IOBluetooth, which will be mentioned twice in today's presentation. This article explains how to write a user mode program to communicate with the Bluetooth daemon and driver, and finally meet the requirements such as modifying the local name, as shown on the left. Here. The author wants to change the Bluetooth local name to CDA. With the knowledge learned by using KMon-based sniffer, this requirement is easy to us to achieve. We only need to implement the calling process from one HCI create, and then read local name, change local name, and then delete. So we can have a command line tool like the one on the right. In the next step, we need to deepen our understanding of vendor-specific commands. Vendor-specific commands on macOS can be divided into two types. The first is the built-in VSCs. Reverse engineering shows that these commands have corresponding handlers and indicators. But more vendor-specific commands come in the form of raw data. For example, as shown in the screenshot of HCI Sniffer, it's raw command in the format of raw command. At this year's Black Hat USA Arsenal, I shared some tools that use the raw vendor-specific commands. They can communicate directly with the controller. Among them, some commands are very variable. They can even read and write RAM data of the firmware. And here is the link. Okay, so our next goal is fuzzing. Because we have sniffers, we can quickly convert them to passive fuzzer. That is because we can do bit flipping of input parameter easily. And we have implement some tools that can send, for example, raw vendor-specific command to controller, which can also be transformed into active fuzzers. In practice, I found that combining the two fuzzing method often has better results. And by the way, since we have Kimon in hand, we can use the inline hook-based method to perform basic code coverage analysis against closed source drivers. Let's say how my fuzzer works on macOS Bixer. Let me play the video. As a target machine, when I made this video, the operating system was the latest macOS Bixer. Let me run my fuzzer, and after a few seconds, the system crashed. It's already crashed. Okay. Yeah. Through all kinds of efforts, we have gone a long way. Compared with simply reading documents and codes, we already have our own sniffers and fuzzer. We even implement simple code coverage tool and the kernel address sanitizer for closed source driver. They are not perfect, but as we will see in the next chapter, they do perform well. The next chapter is mainly about vulnerability case study. I will share with you some details of the latest macOS Bluetooth kernel vulnerabilities and what I have learned from them. Since HCI is open to low-privileged processes, the InfoSec community has always been concerned about the security impact of these interfaces. In recent years, binary auditing and fuzzing against drivers such as IOBluetoothFamily have never stopped. We can also prove this from the output of Adapro Hexray. The routing IOBluetooth HCI user client valid parameters has expanded from 300 lines of code on macOS High Sierra to more than 3,000 lines on macOS Catalina. So that means hunt vulnerability is not that easy. However, with the help of fuzzers, Kimon-based code coverage method and the kernel address sanitizer solution, I did find some security problems in the latest macOS, and so far I reported the 23 vulnerabilities to Apple. And their types include uninitialized memory dereference, kernel information disclosure, heap data out-of-bound access, arbitrary memory access, double-free, use after free caused by risk condition. And one more thing, security update 2020 number 2 can be bypassed. Here is the CVE ID and the patch information. The first vulnerability I want to share with you is related to out-of-bounds reading of kernel heap data. I given two cases for this type. The CVE ID is 3907 and 3908. In the kernel address sanitizer's panic log, we can see that for vulnerability 2020 39.7, our actual input length is only 1 byte, and the vulnerable function will read about 200 bytes out of bounds to HCI request. And here we can see a lot of database tag. They are all created by my kernel address sanitizer, and the call stack is this. HCI request formatted. A similar situation also exists in function HCI write stored link key. This handler mistakenly trusts the user input, and the situation is the same. So in summary, this type of vulnerability is straightforward and easy to fix. The vulnerable handler lacks the necessary verification for user mode input parameters, and with kernel address sanitizer's help, such vulnerabilities are easy to hunt. We have several more cases. The second vulnerability CVE ID is 2020-3912. It was fixed in June this year. This is an out-of-bound access vulnerability, and I listed it separately because, as far as I know, this is the third time this function has been found vulnerable. The first time the vulnerability was disclosed in 2014. That means 6 years ago. And in the link below is a POC for the vulnerability. And then in 2015, a vulnerability named 2015 3787 showed that the function was once again found to be vulnerable. The call stack triggered by the vulnerability is shown in the figure below. And 5 years later, when I was auditing this function, I found that it still lacks effective boundary checking. When the input is malicious magic number, the handler will auto-bound access and panic. In fact, vulnerabilities are found repeatedly for some complex functions. Another interesting case is 2020-9834. It's a Wi-Fi vulnerability I discovered this year. This vulnerable function was attacked 30 years ago. So for such complex functions, it is better to have complete test cases to ensure that all branches can be covered. Case number 3. The CVE ID of the third vulnerability is 2020-9929, which is fixed in September this year. The reason I noticed this vulnerability is because I found that the indicator of function HCI enhanced accept synchronized connection request has changed. On the High Sierra platform, the indicator is this one. But on macOS Catalina, the indicator of the function has changed to this. This string contains several percentage characters, and I have no idea about the percentage character. So this change has brought me many questions. For example, will it introduce compatibility issues? And what is the meaning of the percentage character? And whether are there other new characters introduced? I have no idea at the time. After reverse engineering, I found that percentage means that the pack and unpack routing need to read 5 bytes of the data from the input address. But the problem is that the address can be controlled by user mode. So the following panic lock is a result of setting input address to dead coffee, dead beef. There are many interesting uses for this feature, such as building a more efficient roll hammer based on this vulnerability. Yeah, we can have a try. Next, I searched for Apple SDKs. This is another case where I found useful information from the SDK. In the Bluetooth header file, the indicator input that can be accepted by the pack and unpack function is defined in detail. A percentage is actually the shift key of the number 5, which represents the reverse processing of the data input by the user. So all the questions about the indicators have answers here. As a conclusion, I want to print out the change of indicator actually means that the function of the controller has changed. And new features or changes always mean new attack surfaces, so which are worthy of our exploration. And by the way, reverse engineering plus Apple SDK usually means a better life. The first vulnerability is related to vendor-specific command. Let's start with LWBT. I found many interesting comments when reading the LWBT source code. The comments show that the author does not seem to be very clear about how to handle the Bluetooth event state machine and how to write exception handling correctly. It should be said that this situation is not uncommon. It's remind me that Bluetooth event handling functions are worth of attention. On the macOS platform, the name of this function is process event data WL, and for which I wrote fuzzer and sniffer specifically for it. And with the further research, I noticed a raw command with opcode FCE9, which is not actually documented. This command will cause the kernel event handler to crash. And this is a screenshot at the time. Yeah. So this case reminds me that undocumented commands and non-standard HCI implementations can lead to domino effect. Yeah. Case number 5. The 5th case is an uninitialized memory dereference vulnerability, which is also the first Bluetooth vulnerability I found. The process of discovering this vulnerability is very interesting. It took me less than 20 minutes to find it. And 20 minutes ago, I just decided to open the Adapro to reverse Bluetooth kernel extension. So this vulnerability gave me a great confidence. I can find this vulnerability not because I'm lucky. Because I'm good at kernel reverse engineering, but because I have made similar mistakes a few years ago. The pattern of this vulnerability is like this. Say, if someone writes a lot conditions in an if statement, so what situation need to be covered in the else branch? To me, for this case, I don't know. I prefer to rewrite this code. And let's simplify the problem, this question. If there are only two conditions, like condition A is true and condition B is also true, we need to discuss three cases in the else branch, which is A is not true, but B is true. And A is true, B is not true. And A and B, they are both not true. So if we ignore these corner cases, they are likely to lead potential problems. So now let's look at the real vulnerability of the macOS kernel. The if branch here has two conditions. The number one condition is the kernel must allocate a heap block successfully, and number two is the user input buffer is not empty. Okay. According to our previous analysis, the else branch should cover all three corner cases. But what about the actual situation? Yeah, we can see here. The else branch has nothing. Yeah, this means that attacker can bypass or skip the initialization process of the function validate parameters by only providing the input length. And this uninitialized buffer are then parsed to all HCI handlers. So this vulnerability has been hidden in plain sight for a long time. And some traditional fuzzing methods are difficult to find this type of vulnerability. And one more thing is, I agree with Linux coding style. Do one thing and do that well. Okay, the last one. The last case also represents a class of vulnerability that took 2 patch days to fix. The story can start with the call stack in the article Hacking IOBluetooth. When I first saw the call stack, the only words I could say was wow. With the deepening of research, I found that it contained a lot of useful information in this call stack. In short, after entering HCI, the entry is simple. Is here simple dispatch WL, and the exit is IOBluetooth HCI request start. After request start, the request will be inserted into a queue, and then sent to the controller through the UART interface. My question is, how to protect the data structure in a multiple thread environment? The answer is the command gate mechanism. which hold the lock when entering the command gate and release the lock when the command sleep is called. So please note that we cannot hold the lock during sleep. Otherwise, it means deadlock. Then a new problem comes. After command sleep, the request is not completed by the Bluetooth controller. So again, how to ensure the Bluetooth-related data structure are safe in this window? Unfortunately, the macOS Bluetooth kernel developers didn't consider this situation. And this design issue is very similar to the Windows 32K user mode callback issue. And due to the limited time, I could not discuss it here. Here is a link. I have explored this kind of vulnerability several years ago, and it's very interesting. So here is a panic log of this vulnerability. It's a user after free or double free issue. So as a previous one, vulnerability like 2020, 9928 have been hidden in plain sight for a long time and affect all macOS Bluetooth HCI handlers. Yeah. So and again, this kind of vulnerability is it's hard to find by traditional fuzzer. Okay, the last part, takeaways. The first one, from the perspective of vulnerability research, I want to say with this research as a starting point, I believe we can do more. And from the perspective of engineering, I would say with the help of Kimon project, I believe we can do better. Okay, thank you very much. Thank you for your time. Bye.